Alrighty, welcome to our next video dealing with solutions. Today, as you can see, the theme of our discussion today is going to be probably a word that's new to you. The way you pronounce it is you call it, we're talking about what are called the colligative properties. Colligative properties. And so when we talk about colligative properties, I want you to think about a radiator in a car. A radiator has the job of keeping the engine from either getting too hot, but it also has the job of keeping the car from getting too cold. So the function of a radiator is to maintain the temperature of the engine. And so what we use is we use something called antifreeze. And even though we call it antifreeze, it really is antifreeze because you want to keep the engine from freezing, but you could just as likely also call it anti-boil, because you're trying to keep the water from boiling. And the way that it works is it deals with what's called these colligative properties of a solution. So one of the things that the radiator has to do is its job is to lower or raise the freezing or boiling point of a solution. So think about the normal freezing point of water. Water normally freezes at 0 degrees Celsius. Well, what we're going to do is we're going to basically add some of this antifreeze to the water, and what that does is it lowers the freezing point. So instead of the water freezing at 0 degrees Celsius, it might not freeze until -2 or -5 or -10 degrees. And the same thing with the boiling point. With boiling points, water normally boils at 100 degrees Celsius, but when you create this solution using these colligative properties, what you're doing is you're raising the boiling point. So instead of water boiling at 100 degrees, the water might not boil until 102, maybe 105, maybe 110 degrees, which might be a good thing. It might be a bad thing. A lot of times when we're cooking, our parents will put salt into the water. And what that does is you're now creating a solution. And what it does when you create that solution is you, again, are raising the boiling point of that solution. So again, instead of the water boiling at 100 degrees, the water doesn't start to boil until 102, or depending on how much salt is in there. And what that does is it makes the solution hotter. With a hotter solution, the food is going to cook faster. So when we lower the freezing point, when we raise the boiling point, this depends on the quantity, so how much solute we have in our solution. And that is what the colligative properties are. There are properties of things like freezing points and boiling points that depend basically on the concentration of the solution. So they depend on the number of solute particles in the solution. So a more concentrated solution will have a higher boiling point or will have a lower freezing point. A solution that's not as concentrated, the boiling point won't rise as much as in a more concentrated solution. So there are properties that change depending on how concentrated the solution is. Now let's focus just on boiling point for a little bit. As we know, the normal boiling point of water is 100 degrees. When you start to boil water at 100 degrees, it doesn't matter if it's boiling with lots and lots of bubbles or if it's just boiling, just those little tiny bubbles. The water stays right at around 100 degrees. So because when boiling point happens, what a boiling point actually is when the vapor pressure of the solution. So again, think back to our gases unit. Remember the lab that we did with gases where we had to deal with the vapor pressure of water when we collected our hydrogen. In this case, again, we're talking about vapor pressure. So we're talking about how much pressure that gas gives off. When that pressure is equal to the pressure of the air, so the atmospheric pressure, that's when things start to boil. So when a solution is formed, the vapor pressure goes down a little bit. So when you form a solution, like when you put salt in water, let's say. When you put salt in water, the water is now more attracted to the salt than it was to itself. And so it's harder to break that attraction. And so a higher temperature is required for that vapor pressure to equal the atmospheric pressure. So when you add something to water, it makes the boiling point go up because the molecules of water are now more attracted to whatever you added to it than they were just to themselves. And so it takes more energy for those water molecules to break off and turn into a gas. So therefore, the boiling point of a solution is higher than that of just the pure liquid like regular water. Okay, now how much higher the boiling point is, again, depends on how much of that solute you add to the solution. And that takes us to some math here. So the increase in the boiling point of the solution, so this is the water, let's say, with some salt in it, compared to the pure solvent. Again, the pure solvent is just water. Is right here, is this triangle looking thing, and then TB. First of all, this triangle thing is the Greek letter delta. And what delta stands for is it stands for the change in ... whatever. So in this case, delta, the way you say this is delta TB. Delta TB equals the change in, the B stands for boiling, and as we already know, T stands for temperature. So delta TB is the change in the boiling temperature. And this change in the boiling point, or the boiling temperature, is directly proportional, again, to how much solute we have in our solution. So this is what we would call, this is the original boiling point. BP stands for boiling point. So delta, or TB with a little degree sign, is the normal boiling point. And then this is your increased boiling point. Okay, and when you subtract those two, so again, this, if it's water, this one's normally 100. And this one, again, depending on your concentration, might be, let's say, 104. So your change in your boiling point is simply the 104 minus the original boiling point of 100. So delta TB, again, tells you how much the boiling point has gone up. We call that the boiling point elevation. TB is the boiling point of the solution. Again, that's with the salt or something in it. And then that is the normal boiling point of the solvent. Now, we've got another, we can use this equation now. This delta TB is equal to KB times little m. Now, we're going to talk about both of these, but let's start with little m. As we know, big M stands for molarity, like a 1.25 molar solution. Little m, if we remember correctly, stands for the molality, like a 1.25 molal solution. So the change in the boiling point, or the boiling point elevation, is equal to the molarity, or excuse me, the molality of the solution times what we call a boiling point constant. And the boiling point constant for water is always, just like the gas laws. Remember the gas laws? R is always 0.0821. KB only for water, though, is always 0.51. Not something you need to memorize. It's something that I would give you. But KB for the same solvent doesn't change. So KB, in this case, is 0.51. And then we would multiply that by the molality of the solution. So let's look at an example of this. How might we see this? Here's a question. What is the boiling point of a solution that consists of 1.2 moles of sucrose dissolved in 1.4 kilograms of water? So when we think about our equation is delta TB equals KB times M, the molality. So the change in the boiling point is equal to that constant, which again for water is always 0.51 degrees Celsius over the molality. And then we're just going to multiply that by the molality of the solution. How do we get the molality of the solution? Just like our last lesson that we learned, we take 1.20 moles divided by the kilograms of our solvent, 1.4 kilograms. And then we just simply do our math. So I'm going to go to my calculator here. I'm going to take 1.20 divided by 1.40, and I'm going to multiply that times 0.51. Now, this isn't a very big number, but this isn't a very concentrated solution. So the change in the boiling point I get is 0.437 degrees Celsius. So that means the boiling point is only going up by less than half of a degree, which really isn't very much at all. And again, this is just an example, but notice what the question is saying. It wants to know not what's the change in the boiling point, it wants to know what actually is the boiling point of a solution. So again, we know that the solvent is water. So what we have to think now is, okay, the normal boiling point of water is 100 degrees exactly. And so if the boiling point always goes up, which it does, boiling points always go up, freezing points always go down, the new boiling point of our solution would be 100.437 degrees Celsius. So that is our boiling point of the solution, having taken into account our normal boiling point plus how much it went up by. Okay, now let's talk about freezing points going down. As we know, like on an icy day, what do? They spray the roads. What do they spray the roads with? With a solution that causes the freezing point to go down. So if they know it's going to be a little bit below zero, then they're going to spray some stuff on the road so that the freezing point, instead of freezing at zero, the water won't start to freeze until you hit like -5, -10 degrees. And so then it's safer for us to drive our cars on. So boiling points, like I said, always go up, and freezing points always go down. So that's why we call it freezing point depression. Okay, salt is put on roadways in winter to lower the freezing point of the water so it doesn't freeze until it gets colder. The freezing point of a solution is the temperature at which the first crystals of solvent begin to form in the solution. And as we know, like I just said, the freezing point of a solution is always lower than that of the pure liquid. So just like the other one, you'll notice I'm not going to go over this whole thing again, but you'll notice that it's exactly the same as the other one, except instead of the letter B, now they use the letter F. So the change in the freezing temperature is equal to the new freezing temperature minus the original freezing temperature, just like the boiling point one. And then again, the change in the freezing temperature is equal to this other constant. Instead of KB, we call it KF, and we multiply it by the molality. So in order to solve a problem like this, KB does not equal KF. They are very different, as you can see. If you remember from the water one, the KB for water was 0.51. For water, the KF is 1.86. But you do the problems exactly the same. You're just going to use a different KF for your solution. Okay, so here's an example of this. What is the freezing point of a solution that contains 0.5 moles of sucrose dissolved in 1 kilogram of water? So again, we're doing freezing point. So the change in the freezing temperature is KF times M, the molality. So the change in the freezing temperature is equal to KF 1.86. And again, for water, it's always that number, times the molality. And then to get our molality, we're going to put our moles of solute over the kilograms of our solvent. And so now we can do our math. We're going to take 1.86 times 0.5 divided by 1. And we get an answer of the change in the freezing temperature is equal to 0.93 degrees Celsius. Now again, let's think about what that means. That means that the change in the freezing point is 0.93. And freezing points always do what? They always go down. And so the normal freezing point of water is 0 degrees Celsius, exactly 0. So if it's normally 0 and now it's going down by 0.93, what's our actual freezing point of the solution going to be? It's going to be 0 minus 0.93, which is just negative 0.93. So you're just taking that freezing point and subtracting it from the original freezing point. In this case was 0. All right, so here's what I want you to do. I want you to pause the video at this time. I want you to go ahead and try to solve this problem by yourself. Get as far as you can. You'll notice that I'm asking you for the freezing point. At what temperature will it freeze based on this information that I provide you? So pause the video now, please, and solve the problem as best as you can, and then come back and watch it, and we'll see where we're at. All right, so for this problem, we have a different solvent. It looks like now we're going to be dealing with benzene. So notice that Kf for a different substance is going to be different. It's not going to be 1.86. They give us the normal freezing point. And again, with water, they didn't even tell us that. The normal freezing point we should know is 0. And we want to know what temperature it's going to freeze at. So since it's freezing, I'm thinking delta Tf equals Kf times the molality. So the change in the freezing point is Kf is 5.12 degrees Celsius over the molality. And again, notice my units. It's degrees Celsius on the top, molality on the bottom. And we're going to multiply that by the molality, which is moles of solute, 2.5 moles, over 1.45 kilograms of our solvent, which is our molality. So the change in our freezing point is going to be 5.12 times 2.5 divided by 1.45, which is equal to 8.8. And let's see, this has only got two significant figures, so I'm going to go ahead and stop right there. 8.8 degrees Celsius. Now again, let's think, is that our answer? Are we done? And the answer should be no, we're not. This again is the change in our freezing point. Remember that delta sign is the change in something. So that's how much the freezing point is going to go down by. Remember again, freezing point's down, boiling point's up. So if our normal freezing point was 5.5 and it's going to go down by 8.8 degrees, we've got to go 5.5 minus 8.8. So 5.5 minus 8.8 is equal to negative 3.3 degrees Celsius. That's our new freezing point of our solution. Okay, now depending on how far you were able to get on this, hopefully this kind of gives you a good introduction to how we can find how much boiling points are going to go up and how much freezing points are going to go down.